Hi everyone, let's have now another method for circuit analysis. This time is the source transformation. Let's recall the Thevenin equivalent circuit as well as the Norton equivalent circuit. Also, remember that we reduced the complex circuit into a simple series circuit when we did the Thevenin's theorem. It is a series combination of the VTH and the RTH together with the resistor of interest, which is RL. And in Norton's equivalent circuit, then we reduce the complex circuit into a simple parallel circuit. It's a parallel combination now of the IN and the RN together with the resistor of interest, which is RL. Also, remember that when we solved for the RN and RTH as well, we have the same method in solving for them, and that we removed the load of interest from a very complex circuit and leave the terminals opened and then set all the sources to 0. That's why the RTH and RN are just equal, and it is called as the looking back resistance RO. So we can use the variable RO since RN and RTH are equal. Therefore, when we look at the figure, the Thevenin equivalent circuit and the Norton equivalent circuit, actually this is the Thevenin equivalent circuit, which is a voltage source in series with the internal resistance RO. And this is the Norton equivalent circuit, the parallel combination of the current source and its internal resistance RO when we excluded the RL. So if we look at the figure, the Norton equivalent circuit, if we try to convert or transform the current source into a voltage source, therefore the VTH, when we wanted to express it in terms of IN, is just simply equal to IN times RO. Likewise, when we wanted to transform the voltage source, the VTH, and the RO into a current source, simply we just have IN equals VTH over RO. Or in general, we have these equivalent sources, the voltage source, the voltage in series with the internal resistance, and this is the current source, the current and the internal resistance. Our objective here is to simplify the complex circuit into a simple series circuit or into a simple parallel circuit with the resistor of interest. How to do it? Tips we have here, the tips to conduct source transformation to solve for the unknown. First is we have to take note that the resistor of interest should not be included in the source transformation. For example, the R, there is a current. The unknown is the current in the R, so that resistor R must be retained until we have the final circuit. Second tip, after each source transformation, we should draw the equivalent circuit. Why? To visualize the next source to be transformed in order to simplify the circuit. Third, if we will see in the circuit that there are voltage sources connected in series, then let's combine them and we will add them algebraically. Also, if we will see current sources that are connected in parallel, then let's combine them and add them algebraically. In adding the current sources, we will let the upward current source to be the positive and the downward current source to be the negative. And the fifth tip we have is if there are resistors that are connected in series or maybe in parallel, excluding the resistor of interest, then we have to determine the equivalent resistance in order to simplify the circuit. And to illustrate the concept of source transformation, let's have the example, find the current Ix through the 3 ohm resistor using source transformation. Now we look at the figure. Let's investigate the 3 ohm resistor wherein the current through it is the unknown Ix. This resistor, 3 ohm resistor, is connected in parallel with the 5 ampere current source, meaning the 5 ampere current source cannot be transformed. Okay, so let's have here to look at the other source, the sources. Then we have the current source 3 amperes in parallel with the 5 ohms. So this is a current source. And then we have a voltage source here that is connected in series with the 4 ohms. So which of these two sources to be transformed? So if we look at the unknown Ix, so it's better to transform this current source because it seems more complex if we will convert the voltage to a current source. So we have to transform the current to a voltage source. So let's have to transform current source to voltage source. And then we will draw the equivalent circuit. So what is the voltage? Here, if you wanted to transform the current source into a voltage source, we'll just simply multiply the 3 amperes and the 5 ohm resistor, and that will make the 15 volt source. So let's draw the equivalent circuit. Of course, the 5 ampere is still connected with the 3 ohm resistor because the 3 ohm resistor is the resistor of interest because the current Ix is flowing through it. So at this point, the 3 ampere in parallel with the 5 ohm is to be converted to the voltage source since the current is going to the right. So meaning this is plus and minus. Recall that the current will come out from the positive side of the source. And then we have the resistor 5 ohm to be connected in series with the voltage source 15 volts. So whatever is the value of the resistor in parallel with the current source, that will be the resistor to be connected in series with the new source, which is the voltage source. And then this point, we have the 4 ohms and the given voltage source, the 20 volts. Okay. Now, let's have to observe now the new circuit or the equivalent circuit. We have here voltage sources that are connected in series. So the equivalent voltage source value is now equal to -5. Why? Because this is plus 15 and -20. Plus 15 added to -20, we have -5. Also, the resistors 4 and 5 ohms are now connected in series. We call it as RA, and that is equal to 9 ohms. Okay, redraw the circuit. After source transformation, we have to redraw the circuit and simplify it in order to know what will be the next step. So let's draw the figure. So we have 5 amperes and the 3 ohm resistor, which is the resistor of interest. This is the IX. And then we have the new value of the source voltage, plus 15 added to negative 20. So it becomes minus plus 5 volts. And it's now connected in series with the 9 ohm resistor. Okay, now with this figure, what will we do next? We need to transform, since the 3 ohm is connected in parallel with the 5 ampere current source, so this voltage source will be converted to a current source. So how will we do that? How to solve for the new current source? So you just have to divide it. The 5 volt is divided by 9 ohm. I is just equal to 5 over 9 amperes. So let's draw the equivalent circuit. So this is now the equivalent circuit. Okay, we have the current source, the 5 amperes in parallel with the 3 ohm resistor. And then, okay, look at our figure here. Since the plus here, the plus sign of the source is connected at this node. So if we have to find a current, the direction of the current is like this. Okay, the current always come out from the positive side. So if we convert this voltage into a current source, so the sign of the current will be going upward in parallel with the resistor 9 ohm. 9 ohm resistor. And this is 5 over 9 amperes. We observed that there are 2 current sources. All of these elements, the current sources and the resistors, are connected in parallel. So if we see current sources connected in parallel, we will combine them. So we look at the direction. So in this case, the direction of 5 amperes as well as the 5 over 9 ampere current sources are going upward. So meaning they have the same sign and we just add them 5 plus 5 over 9. If we will compute, it's equal to 5.556 amperes. Then the equivalent circuit will look like this. Okay, so it's positive. So we have here the I total. And we have the 3 ohms. This is the resistor of interest. And another resistor, the 9 ohm resistor. So we have simplified the complex circuit into a simple parallel circuit. Now, since there are 2 branches connected in parallel across the current source, then we can use current division method to solve Ix. Ix is equal to, the numerator will be the resistor of the other branch, 9 divided by 9 plus 3 times the total current source. So if we substitute the values, we have 9 over 9 plus 3 times 5.556, and the value of Ix will be equal to 4.1667 amperes. As you see in the example, that the repeated source transformation can be used in order to simplify the complex circuit. As you can see, we first transformed the current source into a voltage source, and this is the equivalent circuit. After that, we see the voltages are connected in series, so we added them algebraically and combined the resistors, and we have this equivalent circuit. And after that, since the 5 ampere source cannot be transformed since it is associated with the resistor of interest, which is 3 ohm resistor. So we decided then to convert the voltage source to a current source. How did we got it? We just divide the 5 by the 9 ohms. So we have 5 over 9 amperes. Then, since we see current sources connected in parallel, then we combined it, and then we have come up with a simple parallel circuit. Then we solved for IX using current division method.